It's my great pleasure to introduce Mioara Joldes, who will speak about moment problems for holonomic functions. Yeah, thank you very much for coming.
Okay, so thank you very much for having invited me. It's the first time I speak in your seminar. It's a great pleasure to be, even if I cannot be in New York, it would have been nicer to be there. But currently I am in Toulouse. So I work at CNRS in France in the LAAS laboratory, and this is a work jointly done with my former PhD student Florent Bréard, who is now a researcher in Lille, and also with Jean-Bernard Lasserre, who is a researcher here in Toulouse, also in the same group as I am. So this work today is about, that I want to present today is about some moment problems. And I think nowadays moment problems are omnipresent, either in optimization or analysis, and they have a lot of applications in statistics, in signal processing, also in combinatorics if you want. So to define the notations, the setting I'm considering today is moments of measures that are that have a compact semi-algebraic support, capital G, and which have also a density with respect to the Lebesgue measure F, and this density F is holonomic, meaning it satisfies maximally overdetermined systems of linear PDEs with polynomial coefficients. Of course, everything is placed in the multivariate setting, meaning that we consider monomials x to the alpha in n variables x1, xn, and of total degree at most alpha, meaning the sum of the partial degrees of each variable. So when we deal with this kind of moments and measures, there have been a lot of questions answered regarding either what we called the direct problem, meaning knowing the support of our measure and also the density, we want to be able to say something about the moments. More specifically, we want to find a complete system of recurrences for the moments M alpha. When we are able to do that, we also say that this measure is finitely determinate. There is class of works coming from computer algebra and also differential algebra setting, mainly based on creative telescoping. And I could cite the group of Linz, mainly Christophe Couchan, or also some algorithms of Waku or Takayama algorithm, which are able to build a complete system of recurrences for the moments M alpha, starting from known support and density of the measure mu. Regarding the inverse problem, that is, if we are given finitely many moments, how can we reconstruct in the same time the support and or the density F? There has been some work, but this is, let's say, less developed from the computer algebra perspective, and this is more what I'm going to focus on today. Even for the Lebesgue measure, reconstructing the support G when the moments, finite number of moments are known, is quite a challenging problem. Here I just show a very toy example where, for instance, we are given successive numerical moments into variables, and we want to reconstruct this shape by increasing the number of moments. So beside this toy example, there have been a lot of algorithms in optimization or analysis which deal with the reconstruction of support of specific types like convex polytopes, planar quadrature domains, a Sublevel set of homogeneous polynomials, etc. And there have been also some works from the more symbolic or the algebraic perspective, which actually deal with the reconstruction of sparse exponential functions, which boils down to reconstruction from moments of Dirac measures. And there has been also some work done by Batenkov, which deals with the reconstruction also of the density, but in the univariate case, when the density is piecewise definite. So in our work, we were inspired by a previous result of Jean-Bernard Lasserre and Mihai Potinars, who is an exact reconstruction result, meaning that they proved that if our support G has an algebraic boundary, which is cancelled by a polynomial of total degree at most D, then knowing a finite number of moments up to degree 3D, we are able to reconstruct exactly the coefficients of the polynomial G. So this is quite a nice result from computer algebra perspective, in the sense that it is an exact result. There is no numerical approximation, and their key idea was also based on using linear recurrences and also differential operators via the Stokes theorem. Our main, let's say, contribution was to generalize this approach in the framework of differential algebra, in the framework of computer algebra algorithms available via holonomic distributions. And we were able to prove that their result generalizes to also more than just the Lebesgue measure, to densities given by exponential of polynomial. And then we also proposed some generalized algorithms in a more general case, when we consider algebraic supports and general holonomic densities. But in this case, we are not able to give an a priori finite bound on the required number of moments. So now that I have, let's say, give a small introduction to the subject, I would like to firstly frame this problem in the setting of differential algebra operators for distributions. So to do so, let us consider first the skew polynomial or algebra built with the usual commutation rule. Here we are still in, let's say, n variables, which we can also extend to rationals by studying the action of the derivatives on the rational fractions. If we consider the rational or algebra, we can then say that a function is definite when its quotient, when, well, let's say, firstly, the simplest definition would be to say that when the function and its derivatives span a finite dimensional space over the rational fractions. Then by considering all the operators that annihilate, or cancel the function f, we denote this the annihilator of f. And we are usually given a left ideal for this annihilator to, in a way, identify the function. We work with this kind of systems of partial differential equations satisfied by the density. So what does this give on the moment side? So, well, if we look at the moments, what we would like is to build kind of the analogy, and this would be via the shift array algebra, in the sense that if we see the moments as a sequence of numbers and we also consider here the indexes in the variables, then a shift operator, well, it's the obvious action with respect to the ith variable, and then also the commutation rule is given by this equation. So we would like to be able to say in the direct problem, given a left ideal for the annihilator of f, construct in the shift algebra a left ideal for the annihilator of the sequence of moments. In the reverse problem, in the inverse problem, we would like to reconstruct a polynomial that annihilates, that cancels on the boundary of the support G, and also a left ideal for the annihilator of f when we are given sufficiently many moments m alpha. So this would be the problem framed in the differential algebra framework. So how can we work with this? Well, first we have to actually study the action of these array algebra operators on measures. So we would like to look at the measure as a linear functional, and in this case, when I have both the support and the density, I can express it simply by using the characteristic function for the support. So it's just 1 when the point is in the support and otherwise it's 0. So we look at the action of this measure on the test functions phi, and we have the usual formula of the integral over g with respect to the density f of the test function phi. So now let's look via an example on how do array polynomials act on measures. So let's take the simplest possible example in the univariate case, where we consider that the support is just -1, 1, and the density is 1, so we just consider Lebesgue measure. So then our mu is just given by the indicator on -1. So if we look at the action of this measure on test function phi, well, it's of course just the integral from -1, 1 to on the test function phi. So let's test one differential operator on this measure. Well, let's take a differential with respect to x. Then this commutes with the test function in the classical way, and then we get that this is just the integral from -1 to 1 of the derivative of the test function, and of course this is the classical formula, and we get that the action of the derivation on our measure corresponds to building the differences between two Dirac measures at -1 and 1. Now let's derivate again. In this case, we get a derivative of two Dirac measures. So we already go in the distribution class. So we see that the action of these operators is well posed in functions in distributions. So let's take another operator. In this case, if I take x2 -1 times dx, I get by commutation this integral, and since the support cancels exactly on this polynomial, I get an operator that cancels my distribution. And so I get actually that this array operator actually is in the annihilator of my measure viewed in a distributional sense. So I'm able to construct also annihilators for measures. Okay, so now in general, what is the action of array polynomials on such distributions? So we have the commutation via the test function. Here is just the adjoint operator. And then, well, so as I showed, the derivation just is just a negative, and the commutation is done via the adjoint operator. So just one small remark, just that in this case, we only consider the holonomic case and not the definite one, because we cannot divide by polynomials and consider rational fractions. Why is that? A simple counterexample is if we take an operator that annihilates the Dirac distribution, well, this x, the simplest one, x, if we apply just the definition, this gives 0, but so x is in the annihilator of the Dirac distribution, but if we divide by x to cancel to be able to create denominators, rational fractions, then we would obtain, well, that 1 is also in the annihilator of delta distribution, which is of course not the case, because this would mean that delta equals 0. So when working with distributions, we can apply operators like array polynomials and do all the machinery of the usual differential algebra algorithms, but we have to take into account that we cannot cancel out denominators. So we will only work in the polynomial holonomic setting. Okay, so with this remark in mind, if we continue our example, so we have found an operator which annihilates our measure. Then, by applying the linear relation, we just have that this becomes, like I showed before, the integral. And because when we consider a test function as a monomial, wherever degree k, then we get that this translates to a linear relation between the moments, because we only have derivatives and multiplications with respect to polynomials, and this gives polynomials, and then we have the final recurrence between the moments. So, well, of course, we can verify that the recurrence that we obtain is true. So with this process, we are able to, in a way, first create an annihilator for a given measure, and then to apply this annihilator to polynomial test functions and to build recurrences for the moments. So can we do this for other densities? Can we do this when the density is not 1, when we don't have actually just the Lebesgue measure? So in this case, we have, let's say, a Gaussian density, so x exponential of minus x squared, and we would like still to build recurrences for the moments. So we keep in mind this relation regarding the action of the operator on the measure, and by knowing an operator that annihilates the density, we should be able to create operators that annihilates our sequence of moments. So if we only take the pure like operator that annihilates our density, the first one, let's say, then we apply this rule, we get something like this. And the problem is that we get some boundary conditions here. If you can see it also like using integration by parts. So in the multivariate case, this is not nice in the sense that we will have to evaluate this on the boundaries of the support, which is quite complicated. So how can we get rid of these boundary conditions? It's also like in the Lebesgue case. Well, if we multiply by the polynomial which cancels the boundary of the support, then we obtain that the boundary conditions cancel also. So in this way, we obtain an annihilator for the measure mu when now the density is not 1 anymore. So as you observe, how did we do it? We took the annihilator for the density and we simply multiplied with a polynomial that cancels the boundary of the support. And once we have an annihilator for the measure, then we apply it on test functions. And simply by translating the powers with respect to derivative or multiplication, we simply get the recurrence for the moments. So this is the main idea to use, is starting from an annihilator of the density and multiplying with a polynomial that cancels the boundary of the support. We are able to build an annihilator for the moments. So in the general case, it's exactly the same idea. Now we have an annihilator of order R for our density. And what we are saying is that by multiplying with a polynomial that cancels on the algebraic boundary of the support, raised to the power R, where R is the order of our annihilator of the density, we can get an annihilator for the measure mu. And this is simply based on using the Lagrange identity and noticing then that this term here, which is called the bilinear concomitant, is explicitly known, and it contains only derivatives up to order R minus 1. And when we apply this identity, we observe that this term is exactly contains exactly the linear operation of our measure multiplied by the operator that we want to build. And this term can be, it's a gradient and can be expressed using Stokes' theorem as an integral on the boundary of this term. So without actually looking at more in details to this, we observe that just by putting a test function, which is of the form g to the r times phi, this term cancels because it cancels on the boundary, g cancels on the boundary, and the bilinear concomitant only contains derivatives up to order r minus 1. And also this term cancels because L annihilates F, and then we get directly an annihilator of this form for mu. So this is the general case, and we will just use this idea to build now algorithms to reconstruct moments from the given annihilator for the density, or the inverse problem where we want to reconstruct the annihilator once we know the moments. So this is, let's say, more algorithmic view of this process. So for the direct problem, once we know an annihilator, a left ideal for the annihilator of f, we can build a left ideal for the annihilator of the moment sequence by using the translation rule that I just showed previously. And we have shown that the annihilator that we obtained is holonomic in special cases, namely for an exponential of polynomial when the polynomial which cancels on the boundary is not singular. But in the general case, although we reconstruct some operators that annihilate the sequence of moments, we are not able to prove that actually this set of operators is indeed a left ideal for the whole annihilator that could be of the moments. And for the inverse problem, what we do is now we suppose that we know the moments and we put an ansatz on what should be this thing. So we put this like a symbolic ansatz, and we consider that the coefficients of this operator are not known. We solve the system up to an order n, and then we can obtain the coefficients of the polynomials involved in the whole operator g to the r times l, and then extract g and l using the GCDs. Or if everything is given numerically, we have to use some numerical extraction here. So the question is now, can we reconstruct always correctly from solving this system the both G and L? And can we give an a priori bound on the number of n that are sufficient such that this reconstruction is always correct, meaning that we obtain the actual operator, not some spurious solution. So I don't know how much time do I have. I started maybe at 50, something like that.
Yeah, slightly before 50. So I would say it may be good to go for a break in, let's say, like 4 minutes.
4 minutes, yeah, perfect. Yeah,
so I saw you have algorithms and proofs, so maybe you could talk about algorithms and example now, and we can talk about proofs after the break, like this, for example.
Yeah,
would be okay?
that would be perfect. Yeah. That's why I firstly give like more the algorithmic way, and I thought that we could do proofs afterwards.
Yes, yeah, thank you very much. Perfect. That's
okay, perfect. So to go to the, okay, so I will just show how the reconstruction in the exponential over polynomial case works in the 4 minutes that I have, and then the proof for more detail why it works in the general case, we can go after the break. So in the exponential over polynomial, so what we know is we are searching for a polynomial g of total degree at most d, which vanishes on the boundary of the support, and we are also searching to reconstruct the coefficients of p. We know that the density is exponential of a polynomial of at most degree, a total degree s. So as I showed you before, what we do is we make an ansatz. So this would be the unknown exact operator that is in the annihilator of mu, but well, we don't know it, so we make an ansatz on this one, and here so if we would put an ansatz on G directly and an ansatz of P, we would get a non-linear relation between the coefficients of these two polynomials. So we just put for the moment an ansatz on H. So we would like to reconstruct then these unknown polynomials G and H. So to do that, as I showed previously, we solved the system based also where the unknown are now the coefficients of G tilde and HI tilde, and the known quantities are the moments, and these are here because here we have the multiplication with x to the alpha, which gives each time a moment, which is known. And the only thing that's not known are the coefficients of Li tilde. So actually, by solving this system, we recover these coefficients. Now, to be able to recover both in the same time G and H, we will do so we will obtain P from H divided by G. So so as you see here, so G and H are obtained just from solving the system. And then, well, since G P prime is H, we get G by dividing, so here, I should have P prime is HI divided by G. There is a P prime missing here. Yeah. So we have proven actually that that at least 3D plus S minus 1 moments are sufficient to reconstruct for P tilde and G tilde to be the exact solutions of this problem. Where, so just to state that D is the total degree of the polynomial that cancels on the boundary of the support, and S is the total degree of the polynomial appearing in the exponential. Okay, so so let's maybe stop here and then do after the break the proof.
Yeah, that would be perfect. So maybe there are some short questions right now.
Yeah, please.
Okay, so William Sheet is asking in the chat whether the algorithm
I cannot see the chat. Sorry, I'm really sorry.
Let me read it for you. So is the algorithm is related or similar to Laplace transform?
Is the algorithm
related to the Laplace transform?
No, I mean, you could see it also that way. You could see that the moment generation function, and then it would be so the moment generating function would be related. So you could see it as a relation on how to obtain the translation between the operator on an annihilator on the density towards an annihilator on the distribution. If you take the moment generating function and you consider not the Laplace transform, but I think it's a Fourier transform, so it's similar. You could also obtain it that way, yeah, via the distributions. But well, if we don't work directly with the moment generating functions, then no. But we could also have worked with moment generating functions. So I think that we would have used some kind of Laplace transform on the moment generating functions.
Great, thank you very much. So sorry.
Super. Okay, so I will go on with the question of Gleb, if it's okay for you. So he actually was asking how can we prove this bound on 3D, and why is 3D a magical number? So although I try to answer a little bit during the breakout room, maybe I can show you actually the proof in more details. So just recall that what we are doing is we are trying to reconstruct in the same time the polynomial P in the density and the polynomial G, which cancels the support, the boundary of the support. So and for this we solve this truncated system where we put an ansatz for the operator that we want to search up to order n. And we would like to prove that if n is bigger than 3D plus S minus 1, then we have reconstructed exactly G and P, modulo the constant lambda and the constant coefficient of P. So to prove that, we proceed for the proof first in the reconstruction of P. So by solving the system, we know that this ansatz L tilde holds up to order for any test function up to degree n. And we apply this Laplace identity, and it's composed of two terms. So one is what's left on the boundary, and here we have a scalar product between the direction of phi and the direction of the xi, the variables with respect to which we took the derivative, and the normal to the surface G. So of course, this is our P prime x, because it's just derivation with respect to f. So we have now this relation, and now we would like to cancel out this term and also to be able to do something with this one. And as I was telling to Gleb, the magic is to take a test function in the form of g square times this polynomial that we reconstructed. And this has indeed degree 3D plus s minus 1. And if you check here, so this polynomial cancels on this term because, g cancels on the boundary. And also in this formula, we got a square. So that's why we take this to be g tilde p prime minus h tilde to be able to build here a square. And because the density is positive, we get this is 0 on G. So, well, of course, since this cannot be, this cannot be 0, we get this. We get P prime equal H tilde over G tilde. So, yeah, so this means that we have reconstructed P exactly. And for the reconstruction of G, we use the fact that this is just a gradient, G prime over the norm of G. And in the same idea, here we take something to make a square. But this is only requires degree 2D minus 1. So the max is this one. Yeah. So I hope this now if this answers.
Yeah, sure. Yeah. Thank you very much. That's very explicit. But so it sounds like in principle that could be improved, right? So since you have smaller degree on the second step, you may, in principle, you may be able to kind of trade off them, right, and get something 2.5.
Yeah, but so this would imply so the thing is we need to be able to so here I could improve, of course, because I could take only G, because this would also cancel. But here I have to make this square, otherwise. So if I could know something about let's say G, maybe then I could if I know that also inside G this integral is always positive or something like that, then maybe I could straight it to D.
I see. Thank you. But mathematically, is this bound known to be sharp or not?
No.
And do you expect it to be sharp?
In the test that we made, yes, it was sharp.
Okay.
But yeah, I mean, the thing is that here we also took the derivatives with respect to the canonical directions, but you could also consider different combinations, to cancel out. So we could consider other operators here, and maybe that would give a better, if you change the direction, then maybe this could give you a better result. But yeah, if we take here EI, each canonical direction, then in principle on the examples that we had to take I mean, the number was quite sharp. If we were ignoring some, we could not get the exact reconstruction.
Okay, yeah, thank you. That makes perfect sense.
Okay, so maybe you have other questions, or maybe in the time that I have, I can just show you a numerical example if you prefer.
Yeah, that would be great. An example would be great.
Yeah. Okay. So yeah. So it's this one. Oh. So what I'm showing you here is, so this is the density. Well, suppose it's unknown. Okay. So we want to reconstruct this, and we also want to reconstruct the support. The support is given by this. The boundary of the support is given by this polynomial. So there is a subtle difference to make between the algebraic boundary and the topological boundary. So for instance, when we computed the moments here, I'm only computing them on this oval here. And but the algebraic boundary of this oval is actually these two blue lines. Okay, so and it's given to have an algebraic to have a polynomial, we have to take, this is the minimal degree polynomial that we can take, but this includes also this set. Okay, so what our algorithm does is it reconstructs the algebraic boundary, so the coefficients of this whole polynomial. But actually, when we if we compute the moments with more than 10 digits of accuracy, so here I take up to or I plus g equal 18, well, the reconstructed form shape is well, at the drawing level is undistinguishable. So this works well. When I try to like numerically decrease the accuracy of the moments, so let's say I take 4, 6, and 8 digits of accuracy. So what you see in 8 is, so it's the blue ones. So they are the topological, the algebraic boundary is correctly reconstructed. When we reduce this accuracy, well, for 6 digits, we actually get a reconstruction of the topological boundary. Yeah, which, and when we decrease even lower the accuracy, we get, well, something that is more and more approximative compared to, yeah, to the exact value. But so the algorithm is proved to work in the exact case, but here, well, we tested it with numerics to see how it behaves also, yeah, let's say in practice when the moments are not given exactly. So yeah, so this is something we can get. And well, of course, when we reconstruct numerically the density, so this is the red lines are something we get with when we have the moments with 8 digits of accuracies. We see that, sorry, for the density, yeah, we have a bigger error numerically. Yeah, if we solve the system with least squares or something like that. But yeah, if we solve it exactly, then we reconstruct exactly. Yeah. So
Great. Thank you.
So this is, yeah. Yeah.
So questions to the speaker. So I have some questions. Alexei asked me to ask because he couldn't use the mic right now. So and I also wonder. So first question is like in the actual computation, what's the hardest part? So you have constructing the bound. You have solving equations. You have reconstructing the functions. The GCD part. So what's the worst?
Yeah, so let's say I would say that the power of this approach is that we only have to solve linear systems. So that's let's say that's the good part. So but this system is going to be numerically overdetermined, or because if you solve it exactly, then when you take the sufficient number of moments, then you get exactly the solution. But now, if this system is numerically, you have to do some numerical method. And although, yeah, it's something based on solving over determined linear systems, so we did least squares approximations. These are not problematic in the sense of computationally expensive, I would say that. But I mean, the hard part is to prove that when passing from the symbolic to the numeric approach, we can conserve some good accuracy, or to make some kind of conditioning between how many digits in the moments are sufficient to be able to get a priori accuracy on the solution in the end. So this would be a nice thing to do, but also a hard thing to do. So yeah, so this algorithm was designed to work nicely in theory, let's say. It's a nice theoretical result, and a little bit unexpected in the sense that we can reconstruct exactly based only on finite number of moments. But yeah, the hard part would be to make it work numerically for some applications that currently used other methods that may have better numerical accuracy. I hope this answers the question.
Yeah,
the algorithm is super fast, but the problem is,
I see. The problem is
symbolically
maybe
is nice,
unstable.
but yeah,
I see.
numerically, yeah, what can we do?
Okay, and there's also a question by William about the uniqueness of the reconstruction. So I think the answer is yes. So the Williams is asking whether reconstruction is unique theoretically.
Right.
Like
I probably missed that then. Is this applicable to MRI?
Yeah, so of course, if you want to take the practical, the main practical application, it would be MRI. So the theoretical problem behind is exactly the same one. We didn't test it currently on something practical. So we were more interested in working on this theory of holonomic distribution to get the exact reconstruction in theory. So I don't know if numerically, because in MRI everything is numerical, I don't know how this would work numerically. So I won't say it's applicable to MRI right now. This is more of a theoretical result. But yeah, if the numerical, we need to make a numerical accuracy assessment before saying something about how applicable it is in MRI. I won't put a patient on MRI with this algorithm right now, let's say. Yeah, and the uniqueness, there was a question about?
Well, I suppose it has to be, otherwise it won't make much sense. But
yeah, so that is the point is that we can reconstruct it exactly, but I mean it's the unique solution with a finite number of moments. Yeah. So this is the let's say the nice part, that we don't get any spurious solution and any solutions that are not in the annihilator, the true annihilator of the density or the support.
So how would the change in terms of, well, sorry, let me put it another way. In the algorithm, do you use any relationship among the moments that actually makes it finite? I mean, that doesn't require the infinite number of moments. So there must be some relationship, which is the recurrence that you're looking for, I suppose.
Yeah. So
so that relation was assumed in the hypothesis of the result, right?
Yes. So in the hypothesis, what you assume is that you are searching for a holonomic. So you are imposing these ansatz. You say, okay, what I want is, what I know is that my density is a polynomial of p, exponential of p, where p is a polynomial of total degree s. S is fixed. Okay, that's why that's why the bound depends on s, and also g cannot be anything else but a polynomial of total degree at most d. And then you know that your operator will be something like this, and it's from here that you do this, that you can do this proof, you know, because you have the Laplace, this Laplace identity, and here you by putting the good test function, you can prove that well, the polynomial that you reconstructed cannot be anything else but the exact by the ratio between the two polynomial that you computed. So this is the part where this is the input you have. Otherwise, if you don't suppose that your density has certain form or your polynomial is of certain degree, you can do something, but there will be no exactness, no proof that what you reconstruct is what you were searching for. So that's the input of so the relation between moments actually is hidden exactly here, because when you put these ansatz, this automatically gives you the relation between moments.
Okay, right.
So that's the play is the back and forth between if I have an annihilator for the density in the algebraic support, then I can have this relation between moments. But now, if I put an ansatz of the form of this density and this support, then I need a fixed number of moments to be able to reconstruct, to fill in the blanks, like for everything that was missing in my form, my pattern that I created for the density. I hope this this is more clear.
Oh yes, thank you. Yeah, it's very beautiful result. Actually, very nice.
No, thank you. It's more of theoretical work, because it's based on the work of Jean Bernard and Mihai Putinar, who are more known in the optimization, but they don't work in this differential algebra setting that much. So so we kind of saw their paper and said, oh look, if we put it in this or a polynomial or a algebra setting, that would look nice, and we could generalize a little bit. So.
Does this problem originate from statistics, and how do statisticians work on it?
Yeah, so I would say that there are several origins of this kind of problems. I think there is also, from our perspective, we took more the polynomial optimization perspective. So we worked with and checked more the works on related to moment problems in optimization. But I think in statistics, you have especially it's more specialized on different domains. So it's on polytopes, on planar domains, so I think it's not so much on the polynomial support, this algebraic, let's say this is more from the polynomial optimization, where the tendency is to say, okay, the support is a polynomial. The algebraic boundary of the support is a polynomial. So I don't know if in statistics we are really interested in having supports, algebraic supports. I think what I've seen is more, planar domains or polytopes or something like that. Okay. So I don't know if they use a lot this, but now, well, everything is there are people who work between the fields, so I think there may be some applications also with this algebraic view, but I can't say more. I don't know.
Yeah, there were actually relatively recent papers about also number of moments to reconstruct mixture of Gaussians.
Yeah, I mentioned that in the beginning. Yeah.
So and they also had some bounds, but maybe slightly different.
Yeah,
I don't remember exactly.
yeah, so these guys we kind of I think they worked more or less in the same time as we did, but well, we published
Oh,
first.
I,
Let's say.
I actually meant different people in different papers. So
Yeah, so
uh,
but they are also from optimization, you know, so it's they do reconstruction of Gaussian mixtures, but they are not statistics people, so they are in the same community as Jean-Bernard Lasserre. They are working on in the polynomial optimization field with moments, SOS, and so on. So yeah, so of course the algorithm that we have can be generalized to, so yeah, the exponential of polynomial case is just one example, and then you could, we could reconstruct, oh, sorry, just do this.
but I think there are also a couple of papers by Jean-Charles Fougère, Carlos Amendola, and Bernd Stumpfers also about Gaussian mixtures.
Yeah, but so
yeah,
but
okay.
I won't say that Jean-Charles Fougère is a
it's not
statistics guy.
yeah,
You know,
sure.
so yeah, they are all working in the polynomial optimization, and yeah, so we, if you see Gaussian mixtures that they are needed in statistics, then yeah, then, but it's not practical applications in statistics.
That's true.
Yeah, and what we do can be, I mean, I didn't go into the general case, but Gaussian mixtures are just, they are going to be just higher order.
Higher order, yeah.
They will have a higher order annihilator, and then you will just get, we have, so it's the same strategy. You just first reconstruct the density and then reconstruct the support. But as they showed, I don't know if in their article they show that for Gaussian mixtures you have a bound, an a priori bound on the number of moments. I don't know.
I don't remember that.
Yeah, so this is
just,
yeah, so because if you go only on the support, so you suppose that your density is known, even for Gaussian mixture or whatever density that is holonomic, then you have also a bound on the number of moments you need just for the support. So let's say, yeah, you have the restriction of a Gaussian mixture to some bounded support, then you can reconstruct the support given the moments and if you know your Gaussian mixtures. But if you don't know the same, you want to reconstruct in the same time the support and also the coefficients of the Gaussian mixtures, that I think you cannot get an upper bound. But yeah.
Okay, yeah, thank you very much for clarifying. Any other questions to the speaker? Okay, maybe I have a last very short question. So when you were talking about direct problem, about like constructing the inequality operators, you were computing Gromov basis at some point. Like after you construct the operators, you compute Gromov basis. Why do you compute it? I mean,
yeah. So
special reason?
Yeah. So when you do the direct problem, so from the annihilator of your measure, there is a direct correspondence to obtain annihilators for the moments. But the question is, do you have enough annihilators? Do you have enough to have it the full holonomic stuff? Okay, so for each L1 here in the for each a polynomial that annihilates your density and support, you get one recurrence for the moments. So in the univariate case, you don't have any, it's easy. Okay, you only have one recurrence and it's a good one. But in the multivariate case, you need more relations, and to have a holonomic ideal, you need to have as many as possible. You need a maximally overdetermined system. So when you when we translate all the recurrencies with this just linear transformation, we are not sure, we cannot prove that in the general case the annihilator that we obtain is for the moments is holonomic. So I mentioned the Grobner basis because once you have this, you could try just to use a Grobner basis algorithm, and if it finishes, then you have a proof by certificate that you have enough recurrencies. Now, otherwise, maybe you cannot, you didn't build your whole, your whole annihilator. You didn't build an ideal of your annihilator.
Okay, yeah, thank you. That makes more sense.
Yeah. But for some cases, we can prove that it works all the time. But
okay, so sometimes you don't need it, but as a sanity check, you okay. Okay.
Yeah. But for the inverse problem, you do not need this holonomicity. So for the inverse problem, it works only to create this many linear relations, solve the system, and yeah. So this is also nice in the sense that it's a little bit unexpected. I mean, if you had built a holonomic one, it would have worked because you could always reconstruct, go back. This is like an under the staircase. You have everything under the staircase, and you just from given moments you can just go and reconstruct all the moments. But in general, we don't know that this is holonomic, and it's not needed for the inverse problem.
Yeah, that's very nice. That it is surprising.
Yeah, this is quite surprising.
Hey, any other questions? Good, then let's thank the speaker.
Thank you very much again for the invitation and for the questions. It was really nice talking to you.
Oh, thank you very much. Our pleasure. And